Let's move on to the second segment. We're going to do a little bit of physics here, and I'm going to start with a recap. Okay, here it is. We've been doing distance, we've been doing force, mass, acceleration, and the first thing I want to mention, just to reinforce that, is that the distance of physics, separation, is not the same thing as the distance traveled of mathematics. Very, very important to keep that in mind. Mathematics only has distance traveled. What they do, they unroll the measuring tape and they measure how many meters, how many yards, how many kilometers, miles, whatever. So distance, when a mathematician says distance, he means distance traveled, displacement, movement, change of position, of location, whatever. There's motion. Okay, that's not the distance of physics, which is a static concept, which is a separation between two objects. Distance traveled is one object that moves away from a given an arbitrary starting point. Force in Newton's second law, right? Force equals mass times acceleration. That's push. Okay. Again, you're parting from a point and moving forward. Okay. And what is that? Mass times the acceleration. You're pushing. Okay. And it's a dynamic concept. On the other hand, Newton's gravitational law, those two laws, by the way, were ascribed to Newton, even though he doesn't deserve the first one, more or less. The second one, again, more or less. He didn't come up with a gravitational constant G. He just said, it's because of masses that we're being attracted. That's all he said. It's a description. He never had an explanation. And so the second equation there, force equals gravitational constant G, mass 1, mass 2 over distance squared. That's a pull force, okay? And that's a static concept. Actually, it's not pull, it's a tension, because what you're talking about is two masses, mass 1, mass 2, separated by a given distance. That's all you're talking about there. And so that separation of the two masses is what gives you the force at that location only. If that one of the two masses moves a gazillionth of an inch, all bets are off. Suddenly you have a different weight, which is a different force. Okay, that's an equation for weight, essentially, because you're talking about gravity pulling down on some object. One mass in this case would be the Earth. The other mass, mass 2, could be anything else. Could be even the moon, for all we know. So whenever you're talking about this equation, you're talking about two objects and separated by a given gap, separation. Okay, and so that equation really is an equation of tension. I'm saying what you have there is tension, not force. And tension, no, it is not a force, as the mathematicians have always said for the last 400 years. Tension, nobody wins the tug of war. Force, you have only two forces, push and pull. In quantum mechanics, they invented two more, the strong force and the weak force. We don't know what those are, but they seem to be very similar to push and pull, because the weak force is an outward force, and the gluon, the strong force, is an attracting force. It keeps two quarks together. So again, we have push and pull. So the mathematicians have not invented anything whatsoever under the sun. We still have qualitatively only two forces, push and pull. That's it. There's no more. Tension is neither. Tension means that you stretch the rubber band to the maximum. It doesn't stretch anymore no matter what you do. So essentially at that point you can treat it as an object made of a single piece. Okay? Let me repeat that. You stretch it so much that it's almost an object made of a single piece. And at that point, you have no motion whatsoever. There is no motion. The two objects are just static. They're sitting there, waiting for something to happen. Okay, so tension, no motion. It's a static concept. That's why it doesn't fall under force, which is a dynamic concept. It means something moved one way or the other, push or pull. I hope we got that, okay? Because the mathematicians out there, they say, no, but we studied and we memorized the stuff in college at the monastery. Yeah, sorry. Qualitatively, no. We have a difference between tension and pull, first of all, and tension and force, because force is what? An influence that can change the motion. And that's not what tension does. Tension doesn't change the motion. That's what it doesn't do, okay? It's what? An action-reaction pair of forces. But they talk about forces, again, this definition is the one you get in the dictionaries, okay? Conceptually, from a physical point of view, tension is a tied game. No one wins the tug of war. Everybody's pulling, and at that point, at some point, you stretch it to the limit, and that's tension. You're in a static situation. You have a certain distance, separation between the two objects, measured by, you can say, well, that separation is a synonym of the stretching, maximum stretching of the rubber band, string, rope, whatever you got in between them, wire, coaxial. Okay, and then we went into mass, okay? Mathematics, what do we have? Mass is equal to weight. There is no difference in mathematics between mass and weight because they never found a way of distinguishing between them. The way we determine mass is by weighing. We don't count atoms. See, if we counted atoms, you could say, well, mass is the quantity of matter, and weight is what we get on the, once we put it on the scale. That's not the case. We put mass on the scale. That's how we determine mass. That's why it's measured in kilograms. Supposedly weight is measured in newtons, but nobody talks about newtons. Everybody talks about mass, kilograms, weight, kilograms, or pounds, pounds, bushels, bushel, whatever. It depends on, what unit you want to use. And unfortunately, there's like 7 definitions of mass in mathematics, and they just live with them and continue on as if nothing. And I showed the other day there's like 4 definitions of weight. Again, everybody just uses these things. They say we haven't agreed. Who cares if you agree? I mean, this is a question of science. In science, we do not agree. We fight for our definitions, and not everybody can have the same definition. Okay? If you have your definition, you have to defend it against attacks. That's the way it works. There is no consensus, no democracy, no authority in science. Okay, one person says, I'm sorry, this is, again, this is what one person says. He says, you don't understand weight. Oh, okay, educate me. Let's see, he says, objects don't have weight in free fall. They only have weight on contact, meaning, if it hits a scale, then it has a weight according to this fellow. That's what he learned at the monastery. Mass is a detached approximation for weight. Okay, let's find out. Let's see if this fellow is right, okay? Is even in the ballpark, okay? Here we have. Weight is location specific, okay? Location and weight are static concepts. You have weight for a given location only. You have a different weight in a different location. You have a given weight for a given location only. Weight does not require contact, which is what this fellow is arguing here. Okay? Measurement is not an activity of science. Science, we don't measure anything, therefore there has to be no contact. We don't use our hands or elbows or head or our body to contact something. No, we use our brain. We use our mind, okay? In science, we do not place the astronaut on a scale to determine whether he has weight. In science, we conceptualize weight. The astronaut has weight whether we weigh him or not. Okay? Do you think that astronaut on the lower right there, do you think he has weight at a given distance from the Earth? Well, yeah, he has weight. Is it because we put a scale underneath him and he has contact with a scale and he pushes down on that and says, okay, you weigh 100 pounds here and you weigh 50 pounds over here and 150 over there? No, we don't do that. We don't have to do that. We know he has weight at that location. He has a different weight at a different location. We don't have to know the value in science. There are no observers in science. Okay, and here we show this gentleman that no, we do not have need contact at all. Here it is. Here's the weight of the moon. It's 7.35, 10 to the 22 kilograms. That's how much the moon weighs. Is it because we put the moon on a scale somehow? Is that how we determine that it weighs that many kilograms? I don't know if you can find a scale that big enough, and I'm not sure what kind of contact you used to figure out, what the moon weighs. No, this was a calculated value, okay? And so we do not have to have contact with the moon at all, okay? And in fact, if the moon moves a little bit, here you see it, okay? You can see that since the Earth is, first of all, not a completely round sphere, it's an oblate, okay? It's a spheroid, and it does change its shape as the moon rolls around it, as Mr. Newton discovered, okay? So that's something we owe Mr. Newton. But you can see that, the moon weighs differently as soon as it moves just an inch around the Earth. Okay, so the moon doesn't always have the same weight, okay? The way they should really do that, if they could, is give different weights for different locations. And they could probably do that with the laser pointer, the laser ranging experiment that they have out there, because they can gauge the distance from the moon to the Earth, and that can give them a good clue of what the moon weighs at different locations. They need that distance, okay? Okay, so today we're going to do work. What is work? Okay, anybody have any idea what work is out there? Well, I'll tell you what work is. Here it is. That's my definition. What the new generations don't have. Now, how's that for a definition? I guess that's got to do with extinction, not with physics, okay? And here you have another one, which I have, what the new generations won't have. How's that for a definition for work? And how about this one? This is a better one, maybe. What the new generations don't want to do. I mean, how many people? I mean, they say what they have 10 million jobs and nobody's applying for them. That gives you a clue that there is work out there, but either it's not well paid. People are thinking that it's not worth their trouble. Maybe the guy lives with his mother or his folks, and he's toughing it out. Maybe, I don't know, selling something on the streets or whatever, or maybe on the internet. And so he doesn't want a job that's going to take up all of his time, especially. So he says, look, I value my time. What am I going to get extra if I actually go out there, work, and get a salary, a devalued salary, right? Is that worth my while? Or should I just continue doing what I'm doing now, whatever it is, right? And live at mama's or at my girlfriend's or whatever, and, just live alone. I think a lot of people in the new generation are selecting that option, right? They're going with that option. Okay, but let's see what it is in physics, okay? It says work, force times the distance through which it acts. Okay, so we have a force, and it's going to be applied through a certain distance. And there you have the one from dictionary.com, says the transference of energy equal to the product of the component of a force that acts in the direction of the motion of the point of application of the force and the distance through which the point of application moves. The transference of energy. We're going to be transferring energy, whatever that is. I guess we'll find out in a minute here. What does Wikipedia say? Well, work is the product of force and displacement. Okay, that sounds straightforward. Then it continues. Work, the energy transferred to or from an object via the application of force along a displacement. Again, the energy transferred. Okay, so there you see all these energy thingies moving from right to left. Is that what work is? Just a bunch of concepts being transferred? I mean, what is this thing called energy? And again, I always like to introduce authority so that I can convince you and persuade you and convert you. Okay, and so here it is. We have Mr. Richard Feynman. He says, it is important to realize that in physics today, we have no knowledge of what energy is. And I can only tell Mr. Feynman that energy is not a what. Energy is a concept. What is it? The capacity, the ability, whatever. Okay, that's a concept. So you can't say you're going to transfer energy like these people are saying, or move energy around. You can't transfer concepts. So the first thing we note is that if work has something to do with the transferring of energy, we already start off on the wrong foot. This makes no sense whatsoever in science. Okay, in physics, this has to do with mathematics. An explanation, a physical interpretation in which they're moving concepts. And that's our first notion of irrationality. Irrationality, first notion, or first criterion, movement of concepts. It's called reification. You are reifying a concept and then pretending, going through the motions, like the mime of moving it around. Very scary stuff, okay? Yeah, never do that. They might put you away. Okay, they should put all the mathematicians who do that away. Okay, you can't transfer energy because energy is a concept. And unless you have an object, you can transfer a tree, you can transfer a dog, you can even transfer a house, some of these prefabricated houses, but you can't transfer energy. You can't transfer love. You can't transfer intelligence. Some people apparently have, but in general, I mean. Okay, so what is work? Well, work is performed when a body is moved against a resisting force. Okay, so there you have the little man, he's pushing, and in this case, you have friction on the ground, maybe if that's a refrigerator, for example, right? It weighs a lot, so it's being pulled by gravity or pushed by gravity, whatever gravity is, right? But the point here is you got friction, and so the guy has to push against that friction, essentially, okay? And so work is force, times distance traveled. And again, it's not distance, it's distance traveled. We're talking about displacement here, okay? There's motion. Okay, here we have a little breakdown of that. So we have work is equal to force times distance traveled. What is force? Well, we held that force is equal to mass times acceleration. Okay, but what is acceleration? Well, acceleration has this change in velocity over change in time. And we don't have to go into any more detail with that, just to say that change in velocity in bodies includes distance traveled. There is a distance traveled component in velocity. Okay, and what is that? That's motion. So we have work is equal to mass times motion, which is that portion of change in velocity. And what is the distance traveled that we started out with there? Force times distance traveled. Well, you see it's motion as well. So we have our conclusion. We have work is equal to the motion of motion. In fact, mass is also motion, because what is mass? It's not the counting of atoms. We don't do it that way. What we do is we weigh it. And the mathematicians would like for you to think of mass as a dynamic concept, because like in special relativity, if you accelerate mass at near the speed of light, you are pressing down on the scale a lot harder than if it's just standing still. So what happens is they say mass increases. So they have mass as a dynamic concept because it's moving near the speed of light, and so it increases, therefore it is also motion. So I forgot one motion there at the bottom. I would have to say that work is the motion of motion of motion. Okay? That's a more correct way of stating. So what do you do when you go to the office? What do you do when you go to the rock pile? Well, you are doing a lot of motion and nothing else. Okay, now you know. What is work? But a bunch of motion. Motion of motion of motion. That's it. Okay? But here we have another situation. What if we take that equation, okay, and now we turn it around and put it in a vertical direction? Well, what we have is work is weight times height. Remember, what is weight? That's force. What was force? Mass times acceleration. And what they always use that force equals times mass times acceleration. But now you're talking about weight. And what is weight? Weight is a struggle against gravity, especially if you're pulling the box upward, you're pulling against gravity. Or maybe gravity is pushing down on the box. Some people like to do it with particles, right? Okay. Either way, you're fighting against gravity. That's the point. Okay. You're struggling against gravity. What is height? Well, that's the distance traveled. That's the displacement. In this case, it's a vertical displacement. Okay. So we have work. In this case, it's no longer sideways like it was before. Force equals mass times acceleration. Now we're supposed to use really Newton's gravitational law. Right? You would think, because it's more applicable to what we're doing here. So we would have to use the force in the gravitational law, which is gravitational constant G, mass 1, mass 2, divided by distance squared, which is essentially the distance between the box and the center of the Earth. What is that times? Height. Because what is height? It's not a single value. What you're doing, you have a displacement upward. You're moving the box upwards. And so you're going to look at how much you moved it and say, okay, that's how much work I did. Okay, I hope that's clear. So we have two different types of work. We have one which is horizontal work and one which is vertical work. Okay, and what I'm saying to you is I have no problem with them using the mass times acceleration force for horizontal movement, but we have a problem when they don't use that same when they don't use the gravitational equation for upward or even downward, by the way, because going downwards just make it easier, but you still have the force of gravity, one way or the other. So when you do it vertically, in other words, perpendicular to a plane cutting the center of the Earth, well, when you do it vertically like that, you have to use Newton's gravitational law. That's my proposal. I'm saying the mathematicians never discovered that, and they keep using force equals mass times acceleration for everything. Okay? So why is that a problem? Well, let me show you. Here we have a different situation. We have an inclined plane. Okay, what happens in an inclined plane? Now we have two components. We have a horizontal component and a vertical component. Okay, here you have a little more than maybe 45 degrees, more or less. But you can see what's happening here. You have a vertical component and a horizontal component. And now which equation are we supposed to use? I mean, we have force equals mass times acceleration. That's going to be for the horizontal segment. How about the vertical segment? Aren't we going to use the gravitational law? G, mass 1, mass 2, divided distance squared. Distance between what? Between, I guess, the ball and the center of the Earth. Separation. Okay, for any given point along that curve. Okay, that's what we're talking about. Remember, force, when you calculate for force, you're calculating only one value. That value is only valid for the given distance that you calculated. The next frame of the movie, okay, you have a different distance. Now you have to do the calculation all over again and calculate the force for the new distance, assuming the masses stay the same. I mean, we will assume the two masses are the same. The separation changes. Gravitational constant G is, again, a constant, so we don't change that. The only thing that's changing there is the distance, okay? But the distance is upwards. So you have separation between the Earth and the ball, and you have different values for every single location, okay? So you take all these values, and you can get your curve in mathematics. Okay, so what's the issue here? Well, this is more or less the situation. Okay, here it is, all three of them put together. No, sorry, this is just the explanation here. Inclined plane, okay, work is equal to force times distance traveled, okay? But what happens with a slanted surface that has two components, the horizontal and the vertical? Well, the vertical part, you should be using Newton's gravitational law, okay? Work is equal to force times distance traveled times cosine A. Where did they get that? Well, the cosine A gives you the angle of that slant there, the slope of that curve. Assuming that mountain that the fellow is pushing the ball upwards onto, assuming that were a completely straight line, right? Well, you could calculate through the cosine of A what value to give at each point, okay? So what happens? When A is equal to 0, you have cosine of 0, and that's 1. And that would give you a horizontal. That's if the guy rolled the ball or pushed the ball sideways, horizontally, no upward motion. But what happens when you have it at an angle? Well, they don't use Newton's gravitational law. What they do is they say, well, calculate the angle, okay, and just get the cosine of that angle. It'll give you that slope, and that'll give you the work that you did if you multiply it times force times distance traveled. Okay, that's how they do it. That's conceptually what they're doing. But the issue is they're not taking into consideration the gravity. What they're doing is just calculating an angle because that's sufficient for mathematics. The question here is what is happening physically. That's what we want to understand. Okay, and what is happening physically is that you have two motions, a horizontal and a vertical one. If you did the vertical one alone, you would have to use Newton's equation. They don't do that. They use force times mass times acceleration. And then they get confused because you get people like Einstein. He says, I don't understand why force equals mass times acceleration is equal to force equals g mass 1 mass 2 divided by distance squared, which is essentially the principle of equivalence. And he says, well, I think they're very much similar, but I don't understand why. Of course he's not going to understand why because he never did qualitative stuff in his life. That's why he ended up with warp space and warp time and who knows what, in other words, fourth dimension. No, it's very simple. Under the rope model, I explained it the other day, you have a hydrogen atom, whether it's leaving the Earth or coming towards the Earth at a given distance. Force equals mass times acceleration, which is the push force going outwards, is equal to force equals gravitational constant g, mass 1, mass 2 over distance squared, which is the pull force of all the ropes at that given point, at that given distance or location. Okay, so here we have it, all three of them put together, okay? We have the guy on the bottom, he's pushing his, I guess his refrigerator, pushing it sideways, okay? That's work equals force times distance traveled, no problem there. We have a problem with the guy on the right because they use that same equation essentially, and they should be using the gravitational equation, that's what I'm saying, again, versus distance traveled. And what do you do when you roll something in an inclined plane? Well, somehow we have to make use of these two equations and turn it into, in order to understand physics, right? So that we would have to use a combination of these two equations to understand the physics of it. Instead, what they've done is they said, just calculate the angle, the cosine of A, and you'll be okay. You'll know what the work is. Yeah, that's great for mathematics. It doesn't give us any insight in physics. Okay, so that's, I guess what you can say is the bottom line. We're interested in physics, not in math. Okay, here are the conclusions for today. Okay, we have Math Viz. These are their versions. Work is equal to force times distance traveled times cosine of A. Okay, work uses Newton's second law. Force equals mass times acceleration. Work does not incorporate the law of gravity. Okay, and essentially it amounts to what is it? Push times motion times motion. What is push? Also motion. So it's motion times motion times motion. That's what work is. In science, we do it a little differently. That was the mathematical version. Okay, science we do it a little differently. We say in physics there is a gravitational component. Okay, so that you understand that you're pulling against gravity no matter what. Even if you go horizontally, you have to factor that gravitational pull. They never do it because it's the same for anywhere on Earth, essentially, right? So, you look at only the horizontal component. But keep in mind that, the Earth, every atom on Earth is pulling on whatever you're moving sideways, okay? Keep that in mind. It doesn't go away. And the explanation is qualitative. That's what we're interested in. We're not interested in math, in the numbers. That's all that the mathematicians are interested in. We're interested in the qualitative stuff. We want to understand what the mechanism involves both second law as well as the gravitational equation. That's known as physics. Okay? We need an explanation for what is actually happening in that invisible world. And yeah, you're going to eventually zero in on the mechanism of gravity and realize that it's a pull force, some kind of pull force. And I would say, do this experiment at home, always in the presence of a trained relativist, okay? Just put your arms to your side, okay? And see if you think something is pushing on your arms, or you feel like they're pulled downwards by whatever gravity is, okay? And yeah, you'll feel that you're being pulled. It's easier to pull down than it is to pull up, okay? Why? Because you're being pulled from the bottom, okay? Just like two magnets, you don't feel that your hands are being pushed from the outside. You feel that something is already pulling from the inside here. So this magnetism is some kind of pull force. And in a similar way, okay, as an analogy only, if you put your arms to your side, you feel that, oh man, it feels a lot better when it comes down. Why? Because something is pulling, and pull is easier, okay? You're struggling when you pull your arms up. You feel that something is actually pulling from the bottom, not pushing from the top, okay? At least that's my experience. Maybe you can tell me yours.